Dr. Parthasarathi holds a BE in Mechanical Engineering and ME in Metallurgical Engineering and a PhD in Material Science and Engineering, forming a strong multidisciplinary foundation that uniquely positions him at the intersection of materials innovation, advanced manufacturing, and energy technologies. His illustrious career includes impactful roles at CE, CRI, Karaikudi, TVS Tribology India Limited, IIT Madras, NIT Trichy, GE Global Research, Sastra Deemed University, where he has contributed in several research, leadership, and technology development capacities. He is currently the Senior General Manager Operations at High Energy Batteries India Limited, Tiruchirappalli, where he plays a crucial role in advanced battery technologies and energy material systems. Dr. Padasarathi is the recipient of prestigious international fellowships, including the Boys Cast Fellowship DST India, Alexander von Humboldt Fellowship by again, his academic and industrial contributions include 75 plus international journal publications, 4 granted international patents, more than 10 patent applications, multiple invited talks, book chapters, and numerous classified technical reports from his tenure at GU Global Research, covering domains such as aviation, energy, oil and gas, transportation, and advanced materials. His core expertise spans material science and engineering, physical metallurgy, materials degradation, joining, and surface engineering, and energy environmental systems, which aligns seamlessly with today's session on advanced materials for hydrogen production and storage. And he will be explaining us the hydrogen economy. And his extensive background enables him to provide deep insights into how innovative materials shape the safety, efficiency, and scalability of hydrogen technologies. We are truly privileged to have him with us today. Please join me in warmly welcoming Dr. Balas Srinivasan Parthasarathi. And also, as he is from industrial background, participants may get interactive session and several valuable experience from him. Sir, you may proceed with your presentation.
Oh, thank you, Dr. Bhargavi, for the warm introduction, and many thanks to all the participants for taking time amidst your other commitments as well. The family needs staying back in the evening for this. First of all, let me congratulate and appreciate the team that has uh, actually laid this platform. I mean, got this program going. More so with the drive from the government more towards the net zero. This becomes an important thing. I believe the audience would be faculty members, PhD scholars, could be some bachelors and masters. So I have tailored my talk more as for a non-specialist and more so uh, quite a bit of insights from the industry market front, just to give you what exactly we feel as industry today from what has been talked about in the country. And there could be opinions that can be raised, floated by me. It's personal opinion again. So I may be wrong, I may be right. I just leave it to you to be judgmental and then decide what is right and what is wrong by calibrating with the information available, right? So, based on my understanding, based on my interaction with people, some of my opinions may be different from what the public may perceive. And some opinions on some of the technologies available, some of the technologies that can move on also could be rather described differently by me, again based on my own understanding. I just leave it to you to exercise caution in interpreting and validating the information with people with information across internet with right sources. So with that, let me just get into the talk. Please confirm if my screen is visible.
Yes, sir, it is visible.
Okay, thank you. Yeah, it's on. So it's a theme in the past 3 4 years. Hydrogen is being talked big. It will continue to be bigger in the days to come. And I sincerely wish all that we talk about today. If I may request, can I just mute, please? Someone's audio is disturbing.
We kindly request all participants to mute their mics, please.
You may.
I have muted, sir. Please proceed.
Thank you. Thank you. No,
Make me that.
I don't mean to offend anyone, but the interest of all people, I thought it will be better to have a bit of silence. Thank you. So, as I was saying, hydrogen will be the talk at least for the next 20, 30 years. And as we talk about net zero, this is going to be the one which is playing the role. But with the caveat I start, are we ready? How fast we are going to gear up? And how the hydrogen economy is shaping in India? That's a very critical piece to understand. As I believe the team here, a team of 120, 130, 150 people that I saw yesterday. Again, I thank Professor Swami for letting me attend the session yesterday. I attended one of the sessions by Mr. Brumel and his colleague Ekangsh, and I also was there a part of session by Professor Srikanth. Right, so I really loved the enthusiasm of participants late in the evening asking questions. I just expect something similar today. And, in the context, I believe the team here is a mix of people with mechanical, electrical, chemistry, physics, and, all sciences together. So the reason why I'm saying is that you will hear it in the couple of slides later. So the intent of this talk is to provide a kind of an overview or a bird's eye view on the directions set by the policymakers, government and government agencies, the opportunities that are available for every one of us, from a layman to understand things to technocrats developing technologies to business people take it and market it for the consumers. All that. That's the kind of opportunity that we have at what level where we are and where we are likely to head to. Some insights will be shared. And more than anything, I always look at the challenges, because only if you understand the challenges that are ahead of you, you'll be able to think and then start to come out with solutions. One of the comments or statements made by Professor Srikanth yesterday was lovely. I really was very happy from an academic making a point. Right, as you try to do something, it is not merely a publication, it is not merely a patent or even going towards a startup. Right, at the end of the day, what you need to see is that do I add value to the system? Is it going to be sustainable, as you say in the title? And what's that in store for me as I take the first one and go to the next? So that should be the thought process. And do not ever chase. This comment is not for the the senior faculty. I can still take liberty in putting this as a statement for the junior faculty who have joined at the entry level or maybe at associate level today, and for sure for the PhD scholars and master's students. So don't chase short-term, conference publications, impact factor, all that are, in my opinion, are very, very short-lived. I stopped publishing, serious publishing by 2010. Last 15 years, I just literally stopped. It doesn't mean that I'm not doing research, I'm not working. So the point is that you do it for your satisfaction, you do it for your, understanding, you do it for the society as you translate, even as a small technology, not necessarily on big things. Incremental benefits that you can bring onto the table in the classroom to the students or to people at home, helping them with some kind of improvements, or society at large at whatever level, will be crucial, and that will give every one of us the immense satisfaction. So with that, the initial note, let me get into the substance. Before going into the energy conversion, right? So because as we talk about hydrogen is produced by converting something into something, right? Sometimes you get byproduct, sometimes you get only one, and so on. So for all that, what is required is the power. So most of the time, you look at energy as one side, right, and then power on the other side. So kilowatt, kilowatt hour for us to remember the terminologies. So if you look back, what we were way back in 2010 and what we are today is absolutely stunning. If interaction is okay with you, if somebody can pitch in, what do you think our scenario was way back in 2010, and what is that in today's context? As India, as a country, what are we in terms of power generation? Anyone? Quickly, one or two answers. I just move on. I always love to make it, two-way traffic, but I know physical mode. If you are present in a classroom, it is easier to do. Online meetings are a challenge, but still, I would like to take one or two answers to move forward. So, Swami, is that okay, or I'll just move on with my talk?
Yes, sir. Please proceed, sir. No problem.
Right. Okay.
Yeah.
So in 2010, if you look at this data in terms of power generation, we were a country producing roughly about two-thirds of this. The installed capacity was about 170 gigawatt. That's the number. So we were, in fact, the power deficient country. Those times. Those who live in the south, especially Tamil Nadu, would know that 2011, 2012 period, there were power cuts for 10 hours, 12 hours a day. It was painful, right? So it went on to topple a government for that matter. On a later note, if I say. So we were a power deficient country, and the renewable part of it, if you look at it, is extremely small, right? It's about just less than 10% is the renewable. And 10 years from then, you see the jump. We have progressed significantly. 370 gigawatt is the installed capacity. The coal contribution remains the same as 50%. But you see this renewable, including hydro, has picked up, momentum. But what you need to see is that what made the change. 2014, some of you would remember the coal scam, coal allocation, allocation of mines and so on. That was the one which changed the entire power sector paradigm, right? So the coal mines that were allocated to specific power plants were actually cleared up, and then anybody can get from anyone kind of a thing. So the plants were not made to suffer, not to wait for the coal to reach them, and so on. So the continuous power supply started, to come from the coal power plants. Renewable increased, and eventually, if you look at 2025, this is the data again. All these from the government websites, Central Electricity Authority, CEA. Those who are electrical engineers, professors, industry people would know this. CEA is the place, Central Electricity Authority. You can get the complete information on India's power plant landscape, including the plant details, capacities, how much produced, how much of gigawatt hour produced per year, and so on, or terawatt hour, so to say. All these available. Look at the landscape of 2025. Obviously, the renewable has significantly marched up, made it 50-50 today. And as you see here, the government's vision, the target is, 2070 is our net zero, right? As we talk about, completely decarbonize and then move towards a kind of a clean environment. And the many other countries have got different, points. I mean, for the net zero, some of the European countries even talk about 2035. Some of the Scandinavian countries, even 2030, they will come close to 90%, they say. And even countries like Germany, which is said to be well, developed, they in fact buy time until 2045 or 48. So it doesn't mean that countries that are actually well developed need to go towards this net zero quickly. It doesn't matter. It's all about the conviction. How do you take this from the economy perspective, how do you drive it? So Indian government has taken a stand to push it by 2070, and of course the oil companies, have decided to do it by 2047 for the two scopes they have got. So it has got three scopes: scope one, two, three. So some of the mechanical engineers or energy enthusiasts would know about it. If not, it is an opportunity for you to go and then know about it a little more. So oil companies have got their own mandate, taking this in their head by 2047. This Vikshit Bharat time frame, they wanted to go and achieve what is for those two scopes. They want to go for net zero. So towards the target, one of the key message, or rather the kind of milestone points given to the country, is that ramping from 470 500 gigawatt as of today, it has to be pushed to 800 gigawatt of installed capacity, and possibly 60-70% could be utilized from this, because not normally the complete installed capacity is utilized. And what is the most striking is that from 230 gigawatt, it is literally pushed 2.5 times, or more than 2 times the renewables to 500 gigawatt. Fortunately, Indian landscape, is so beautifully, aligned to take up these, and with the technologies developing big time, both in solar and wind, and the kind of windmills today we got way back in 2010, the kind of windmills we had were small mills, kilowatt levels, and from possibly tens of kilowatts. Today they have got megawatt or windmills available, and wind farms in a given place can be designed for larger capacities. So with that drive, the country is launching itself towards net zero. And why I'm saying is that these numbers are actually coupled to your hydrogen goals and hydrogen missions, as you will see in the subsequent slides. What you're going to see, as a striking thing in this slide, is that the nuclear has never picked up in the country, right? So right since my understanding of energy goes way back in 2000 2001 until this date, the push in the nuclear segment is pretty marginal, right? We were about 5.5 gigawatt at 2005 frame, and today 2025 20 years down the line, we are something like 8 gigawatt, not much, right? 8,000 megawatt, and that too after adding a Kudankulam plant down south a few years ago, right? So which means that our drive is more towards the renewable. Hydro, there is not much of a push. You can't go beyond a point. That's where the stumble block. I don't think we'll have any big thing to go beyond 50 gigawatt. We slowly ramp down the coal utilization, and of course, most of you would know the NTPC's coal power plants that were installed before 2010 or more or less made to slowly shut down, and beyond to 2015 and until this date, those plans are actually asked to have kind of flexibility and some freedom until they are made to die. They are given an extra cushion for their emissions. Otherwise, the new plants that are coming up as only as supercritical plants. India today, if you are going to produce a plant since 2018 or so, all the plants should be only supercritical, and subcritical plants are not permitted as large scale. And these supercritical plants are typically either 660 megawatt or 800 megawatt capacities as tower boilers. So period. And of course, we have got challenges with the coal, Indian, Indonesian, Australian coal, and that governs the emission norms. But irrespective of it, the expectation from the government today for the coal power plant operators is to have the emissions at extremely low level, be it SOx or NOx or particulate matter, all that are in line with the Paris Summit regulation, and extremely stringent. I don't want to spoon feed the numbers. It's available for those who are interested, would to go and then look into. So with that as a context, that India is today a power surplus country, we have enough that's available for for beyond the current utilization by people, right? So we also see that the government claiming that every village is now with the power and so on. But still, if you go and then dig deep, you'll see that there are remote villages, tribal regions are still even without power today, and people are trying to help them out with the kind of different kinds of powering mechanisms and doing this. So since the topic is related to hydrogen, I thought I'll just post this thing. Most of you should be aware. Hydrogen and Fuel Cell Day is, celebrated or observed on 8 October. So, with the obvious thing that 1008 indicating the atomic weight of hydrogen 1.008. And incidentally, this came into picture since 2015. For many of you may know, some may not know, but you should understand the context. What I am saying is that we globally, right, not Indians, globally, this was driven by the DOE, right? So Department of Energy, the U.S. Department of Energy, with uh, the consortia, industry consortia, pushed it in 2015, called it as the National Hydrogen Fuel Cell Day, the 8th of October, and this year was 11th year. I made this slide, some of the slides for that, so I thought I will make use of it to create some degree of awareness on that front as well. So if you talk about this being pushed in 2015, probably the similar time frame, since there could be many mechanical engineers. Today we talk about Industry 4.0, right? Manufacturing, right? So Industry 4.0 encompasses everything from IoT to today's modern day artificial intelligence. With that involves machine learning, deep learning, all that together. So from 2015, 2011, 2012 was the time frame when the idea was pushed. 2015, the German government pushed a bit on the uh, Industry 4.0. Very similar time frames, hydrogen was also projected to be big. But if you look at the Industry 4.0 today, it's a phenomenal level, right? You can't really imagine any big factory without those, the data processing, digital twin, all that in the manufacturing. But if you want to look at hydrogen at that level, honestly speaking, no. That's why I'm saying I will be having my own viewpoints, and certainly we are lacking big time on the hydrogen front. With the hope that at least at some point in time, with more research impetus given by the government to the organizations, to the industry, to the academia, and more so people with the research bent of mind start doing it and then develop technologies which are going to be efficient. And at that point in time, probably this could be realistic. And we are hoping that with the kind of push that has come in, another 10 years, we could see some light of it. But the reason why I'm saying this 2015, comparing with the, Industry 4.0, comparing that with this, and then, on the progress, hydrogen is not a new topic for that matter. So the gentleman seen here, Arno Evers, is a German, studied in Hamburg University, right? So for a short time, he joined the course apparently from his LinkedIn page. You see this gentleman quit after a few weeks because he was taught metallurgy, steel. And I was laughing looking at this slide because I'm a metallurgist by training. I consider myself a steel expert, at least claim on paper, right? So I'm this gentleman from School of Electrical Electronics Engineering was taught a course on steel, which he hated and then quit. And he went on to do something on his own and eventually become part of Airbus doing some activity and become a kind of a project leader manager. And beyond that, what he did, was so interesting. These guys were the one, the group exhibits was the one started by him. Today we talk about a lot about incubating startups and so on. So I'm not a big fan of all the startups. Genuine technology should move on. I agree with what Srikanth said yesterday, right? So this is one of those things where they were, they were identifying hydrogen as the economy and fuel cell to be doing. And enough of activity in 10 years. He had made a mark. If you go and look at things, incidentally, 2003-4 is the time frame when I was in Germany first time on my first fellowship. So I went to a conference because the institute that I was associated with was working on the metal hydrides, and one of my colleagues was collaborating with me on metals. And then I just went to a conference. I didn't know at that point in time that I would work on hydrogen 20 years later today. It was quite surprising, and I thought I should add the slide. That's the reason why this slide is here. So the point I'm trying to convey is that hydrogen is not a new topic. Way back in mid 90s to mid 2000s, people have tried, and I think all of you should know or must know by now that both GM and Ford, they had their big efforts in hydrogen and fuel cell. Big time fuel cell essentially, and they had attempted that in the cars, trucks, bigger vehicles, and eventually figured out that cars and the small things will not work, and they are only deployed in heavy duty large trucks in the US today. So they also calibrated, and where it can be used, where not, where done, and they somehow eventually some of them pulled out of the race as well. So some of them who are fuel cell manufacturers, continued to be there. Many of them pulled off, and incidentally, this gentleman beyond 2006 did not do much, and then he also pulled off when that wave went off. That was very interesting state to know. And look at this picture. Europe is really a fascinating location. To tour around. I had the privilege, to stay there with the support of Indian government and German government, to tour many places also as a fellow. And one of the great things about is the kind of networking, to knowing people. And this is an example that I'm giving you. Even though those countries, there is not much of real need to move towards hydrogen because they are already onto predominantly into renewable systems, big time, right? So they are big in solar, even though the country is cold and so on. Even under those conditions, they got a good amount of solar system in place, good amount of pumped storage, extensive, renewable side of wind engineering. So, but still, hydrogen is being talked about there. They have European countries, many they have shut down their nuclear operations, barring France. Many of them have closely shut down. Germany full shut, and they are dependent on coal. They don't want to, and eventually they are also going towards this thing, and eventually as an alternative to the electric vehicles where they need to charge from somewhere, they are looking at these. So the point is there is an intense effort across the globe, and more so Europe. I keep it because that's an happening market. Barring again, you just go back to the American, they're in their own style. They have their own pace of handling things. Here it is more of a consortia, European countries under Euro, they form and then they do it. Yesterday there was a mention by Brumil that the European consortium in India floated a call for hydrogen proposals, especially for biogenic waste and so on. I happened to be part of some of that, the panel, and it was very interesting to see the kind of the quality proposals coming in the chase from the different countries. It is not one country, right? It's a consortia having 15, 18 institute, industry, startups, and whatnot. So the message is that globally hydrogen is being pushed, and a lot of knowledge exchange happens. If you get an opportunity to fly out with some kind of funding from AACT or anyone, please just do that. The learning curve will be much bigger. So, talking about the global scenario, we need to talk about India. So, Indian scenario, the first India's refueling station was inaugurated way back in 2015 by the then Petroleum Minister Dr. Manishankar Iyer. So, it was by IOCL. IOCL had that thought then, 2005, when the Western worlds were building and we were not even the race. So this unit is still there in the IOCL R&D Faridabad. Still, some of the ministers, big ministers, cars are the fuel driven, and hydrogen fuel driven, and they are being the fuel station is doing that. You'll see in the later slides some of the development that the country is looking based on the earlier experience. And the point to be remembered is that India was not far behind. Indians despite the famous saying that we are 20, 30 years behind the Western world, We are not really at this point in time. So, but it was happening in a very remote location, which many of us would not know, because today we are well connected. What is happening in the Western world, 10,000 kilometers away, is in your hands in the next few seconds. But that was not the case in the early days of mobile technology and so on. But it was there in those times. And what is more interesting is that this I figured out only when I was making the a presentation for my colleagues on the hydrogen fuel day. So I was trying to figure out curiously when India started to look into the thing. Today I know that there are vehicle buses being run in the Delhi, right? So Hyderabad, Ashok Leyland has stepped in, and people are trying to run some preliminary buses. But you look at the literature, this has come in part of a journal, Elsevier journal publication as a news item, and which probably we would have ignored or missed. Our interest was only to search the literature, not to go anywhere, right? So if there are some old timers, 55 plus or 60 plus in the meeting, they would know the value of using an abstract card or going to the library, reading the journals, reading also the advertisements in those journals. So today we are all focused. Put the keyword, take the only paper and read the abstract, read the introduction, conclusion, and then start writing the paper. So the point is, there were information available on the progress. Ballard is one of the biggest corporations on the fuel cell technology. They were putting in fuel cell with a given specific kind of stats for Tata Motors way back in 2013. Those initial demo were made in the 2013 September time frame. So meaning that 9th March 2012 was the announcement or publication open domain, and 1 year later they looked into it. And look at this showcasing of this by the Tata Motors called the Star Bus, a beautiful bus, with the two door, with a beautiful capacity, right, with about range of 300 kilometers, 75 kilometers per hour, and with the Type 3 bottles they can operate. Yesterday, Drumel was mentioning about Type 1, 2, 3, 4. He did not mention 5. Add that 5 also, right? So this is now today it is possible, but remember these are not available in India. Today we are dependent on some of these hydrogen cylinders. Still, we are dependent on the Western world. Interesting aspect is that high-powered vehicles are available. We are having local stations, HRS as it is called, hydrogen refueling stations. There are bigger plans by the government oil consortia. I will talk about that later. And we are now ready with the buses. And if you look at the literature or open domain information, way back just 3 months ago, I mean, not so long, just 3 months ago, the NTPC's plant has put out its own bus on commercial mode in some northern part of the country, right? I don't remember the name, so I just saw the news item 3 months ago. I thought I should put it, but I forgot to bring it. So I just leave it to you to figure out. So setting the tone, hydrogen technology is not anything new. Western world tried, converged, aborted something, continued with something. Today, the American trucks, majority of trucks, large trucks are with the fuel cell. There are well-established protocols, process for manufacture with reliable fuel cell. There are enough of hydrogen generation facility, which is being talked about here. The hydrogen can be of different color as it is being coded based on the processing route method by which it comes in. So the current practices are produce the gray or brown, which are either by SMR process, steam methane reforming, or by coal gasification, or through the simple pyrolysis process to get to a turquoise hydrogen, or use any of these, but with carbon capture. It's a carbon sequestration as it is called. Some of the chemical engineers in the room would know the term, importance of it. Very significant from the oil and gas perspective, carbon sequestration. So because that's the footprint we are concerned about, and then once that is made, it is a far better thing. It is equivalent to green, I would say, but unfortunately the price points are high because you are going to have the additional cost coming from the carbon capture point of view. So the green hydrogen, as we talk about, predominantly coming from the electrolysis, as we speak in general, water or alkaline electrolytes, so to say. And of course, if you are going to use the grid power from the coal or something else, it is not still green. Using renewable energy, if it is going to be connected, it's going to be called green. So again, there are demarcation within this, green and yellow. If it is any general statement is renewable, any general renewable is called as green. And if it is done through solar, it is called as yellow hydrogen, for your information. Just put in the back of the mind. So an academic stuff here. So steam methane reforming process, a high temperature process where it is being reformed, followed by shift conversion where the CO2 reaction take place, take out hydrogen and then capture CO2 differently. So on the top, as you could see, let me just get the. So what you see is the high temperature process, where it's going to be a gasification part, very similar shift conversion, and you get hydrogen out there and quite a bit of CO2 emission. That's why it is called as brown and gray. And on this side, the same carbon is being captured as carbon here, which is going to be a useful material. You can convert it into this into graphite, graphene, and whatever form it is. The methane getting into this route, reforming route, is getting into pyrolysis route to get into this by splitting. So this is certainly a clean, hydrogen referred as the green. Nuclear, people call it as pink. I'm not bothered to talk about it because nuclear per se in India is very small. But this is the one people talk so big about, the water electrolysis or alkaline solution electrolysis, depending on the kind of electrolysis you use. Could be solar, could be wind, or any other renewable, could be tidal, whatever energy that you can pump in here, as long as that's green, your hydrogen is said to be green. And the mission by the government is to get more green hydrogen in the days to come. So looking at the global scenario first, if you look at hydrogen, it's not something very big. In my opinion, 100 million metric tons is not so big, right? So 2023 data, and the world is pushing to only by so 50, 60 metric million metric ton only. So 160 million metric tons of hydrogen by 2030. Look at India. So Indian thing is today we are at 7 million metric ton, predominantly grey, and we don't have much of footprint of green. And we wanted to jump 3x 2021 25. The 15 to 20 is the band. You talk to any industry leader in the oil and gas sector, they say 20 is the number given. Our target is more. I mean, we are identifying more and more and push it, right? So at least 3x is the number they are looking at, whereas the globally the ramp is not so high. So which means India, because of its advantage from the geographical front, with the abundant availability of the landscape, and more so favorable locations for both solar and wind, we are poised to do better. And if you remember from the earlier talk, out of this 15 to 20 number they talk about, they want 5 million metric tons of green hydrogen by 2030. Today we are hardly a fraction. We are talking about 5, which is mind-boggling. So whether it is possible or not, only time will tell. But the government is pushing, industry partners are getting aligned, and it is moving. At what pace, we need to wait and watch whether the pace is right enough to go to achieve the targets. So when we say this that this is the target, this is what we are aiming at. Why we should do that? What are the opportunities? You look at it, the carbon footprint obviously will come down. Look at some of the pollution levels in some states, and of course the global warming numbers being talked about, all that. So the moment you start slowing down the carbon emission, we talk about so many million metric tons of CO2 emission every day from each plant. Power intensive plants like cement, steel industry, they also are going to be playing a big role for us to get to this level, right? So hydrogen should be there, part of their deck also. So the opportunity is that as you can look into it, a carbon footprint can be big time managed, and then that's going to be a huge plus. Second is the storage and transport. If you look at it, so it's a challenge actually. It's not that easy. So storage, you don't have much of bigger options today. Multiple routes are there. I'll touch upon later in this segment. And of course, transportation of hydrogen is not possible as hydrogen. You have to send it as ammonia or as metal hydrides and so on and so forth. Again, it calls for one more reversal at the site. And the third, as a challenge, as you can see, is that the efficacy in economics today we are not in terms of economics we are not ready. All of you may be aware that one of the goals set by Department of Energy (DOE) is that 111 goal. So it's called as $1 per 1 kg of hydrogen in 1 decade. So this statement was put out by the US government. Of course, it's a government mandate. DOE puts that out, and it was 2021. So by 2031, they want the hydrogen price to be $1, meaning that today's Indian economy it's about 85 rupees. Are we there? No way, we are not there. With all the subsidies, we are not there. So economics part of it, we need to see how much I need to spend for converting water into power, how much of other overhead that I put in, and how do I manage my profit, how do I sell it. So economics today we are not there. That's a huge problem. And the efficacy, of course, efficacy comes with the system. We don't understand the hydrogen system as a whole, be it electrolyzer, be it a fuel cell. Even today, we are dependent on the monopolies. For example, Nafion membrane from DuPont, right? Some of the ionomers used in this from them. Some of the catalysts from some specific countries, specific companies. So India needs to invest as a country a lot of money promoting research at root level, make the younger generation to invest their scientific knowledge and then generate. Right. So unless that is done, we will be just behind some Western world, get the technology at a higher price point and run it. Today, the prices of these units are high because monopoly. If you look at the opportunity, the growth in renewable is the big one. We talk about from 230, we are pushing to 500, and all the renewable is not going to be necessary for us to use. And part of renewable could be 20%, 30%. If I can convert that for hydrogen production, that will be phenomenal. Actually, green hydrogen is going to be huge. Government is supporting big time the kind of the PLI, the schemes that Drumil and Akshansh yesterday described about it. How much of that can translate? How many can benefit? Those are all million-dollar questions. I don't want to talk that as a political statement, but government is trying to help. If there are right set of people approaching right kind of consortium or forming groups, go with the right kind of proposal, convince the leadership or the top level people who are deciding, and get technology, and then you can work on. So on that front, there is no dearth of money. There is enough of money that's being available in different forms. As academic institutions, you have to look at the different portals, look at industry next to you, and then go with as a kind of a proposal as a product, not as a kind of a academic proposal. Academic proposals are no more relevant in the Indian context, in my opinion, right? So I've been part of some of the evaluations, some of the discussions. So very clearly, the mandate is that we need proposals that bring value to the society. It should have some kind of applied research into it. Majority of instances, it doesn't mean that we are not going to support. The government is not going to support fundamental. Yes, it will be there, but the proportions are going to be significantly different for applied research versus fundamental research. So the last thing is that the trade advantage, like any other market, Indian market is said to be, labor, cheap labor as they call, which is one of the worst things I wanted to hear. I would say our quality of labor. When I say labor, even a scientist is a labor, and a workman is a labor, a technician is a skillful person. So cheap is a very very bad thing. Unfortunately, our the rates are lower, right? So the salary structures are different. So people Western world dump money here and then get things done. But At the end of the day, when you can produce and then if you can do an export, you can get a market and further you can keep a price, right? So instead of them producing at $2, you can produce at half a dollar and sell at $1.50. Still, it will be good for them. They can buy any product. I'm not saying hydrogen, anything. So the trade advantage is humongous, and that's where the country looks at this as an opportunity and then has come out with a mission. So this slide, in the interest of time, I'll just flash it for a minute and then leave it. The point I'm trying to drive here is that the thing has been pretty steady the last 3 to 5 years. Even go back, this was the number 1995 is the band, from the global context, and then they had a small amount, and then the intent was to look at newer things. That looking at this in the steel making industry. So it is the DRI, as it is called, direct reduction of iron ore. One of the promising things that people look into it. But again, hydrogen price points should converge there to get into it, and many other process energy intensive processes that are there, like cement or paper and pulp or any other industry. They would be happy to look into it. And this is the number that you will be happy about, right? So the global distribution, and of course, these guys will be there everywhere, big in numbers. India is not far behind. We are still using quite a bit of it, owing to the big oil and gas segment, refineries and so on. They use quite a bit of it, and very small levels on the other side being used. So this slide was presented a little differently in yesterday's session by Drumel. My flavor is a little different for you. So look at these numbers: 20,000 crores being let out. That is one part of it. How much is going to go to the individuals at what level? They call it as multiple schemes, right? So he mentioned about the different kinds of schemes under site, and for development, development, research at different decks. Research component is very small. The industry is being pushed to put large size plants, come up with a collaborative thing with indigenous content. So the expectation from the government today is that they don't need 100% indigenization. They want a kind of part of indigenization. Some portion of it can be local work done. So you can buy, process system, material, even equipment from outside, and assembly system level integration can be done, and the plants can be put out. So today, all the plants that we talk about today in India that have come up in multiple places, including the NTPC, is big thing, and many of the hydrogen valley driven programs, right? So there are multiple hydrogen valleys: Pune, Rajasthan, Bhubaneswar, Odisha, Hyderabad is the recent one, Andhra, right? That's a big one. I think it is Vizag or Hyderabad, one of the places where there is a huge, 10 gigawatt power coupled to the electrolysis system, and there is the Cochin Valley, which is also, equally big time, Trivandrum, Kochi Valley. So government is trying to push more of this, promote more startup, make more companies to come and participate, with a view that it's all about move towards green, decarbonize, promote indigenization in as many aspects as possible. Unfortunately, as far as the membranes or the electrode plates or some of the catalysts, all these are today monopoly. We still buy from one or two sources. Globally, a few countries are mastering it. Of course, China, they've got enough of multiple sources. Unfortunately, some of the government mission programs do not permit Chinese products to be used there. So we look up to Korea. Korea is the one reliable and workable source for the country, for research as well for the scaling up. The US market is absolutely open today. They are willing to work. Many of the MNCs are already there in India. Yesterday they mentioned about the company called Omium, which is in Bangalore. In fact, the Omium is owned by a person by name Dr. Chokkalingam, who is a alumnus of CECRA Karekudi, 97 or 96 batch, BTech. So they have started this company in the US, and then they put a gigawatt plant there. And of course, they have not gone big time. It's almost 1 year they are figuring it out how to take it to the market. The market is not that easy. So please remember this. So the idea is that indigenous manufacturing, look into the country level emission control, look for more employment. People talk about employments every year, at least close to 80,000 to 1 lakh. Employment. We need to develop awareness in people, skilled labor, and the people at the supervisor level, people at the technology level, people at the leadership level, people working on safety systems exclusive for hydrogen, all that to be combined. So in that context, the academia should actually push a bit, more themselves to go understand what it is and learn, and then train, develop more engineers for the world, because training them in the industry is very difficult. The moment a person comes to an industry, they are expected to start the job from the day they get into the work. So it's not easy for he or she who is coming to get into that. So please keep in mind, in case if you are a domain expert, if you can add a kind of a module or two or three in the academic curriculum, or a kind of an elective, or as a kind of value add course, please do that. And talking about this hydrogen, it need not necessarily a simple 5 million metric ton of green hydrogen from renewable. People also talk about the value chain of all those waste, the biogenic waste which cannot be reprocessed. So we people talked about gas, right? So biodiesel, biogas, that's one direction. And these biogenic wastes are those which the waste which cannot be further processed beyond that, and that's the last part of it. It's like incinerating something, and you take them and then produce hydrogen directly from there, with the control, with economy, all that, and that's a big space. This involves, as they talked about yesterday, photochemical, thermochemical, charring, many techniques, right? So we people use all that and then try to get hydrogen, put back that to the economy. So the kind of waste, the people call it as MSW, municipal solid waste, the waste from forests, waste from everyday usage, including the plastics, right? So people talk about that, segregate, and then make use of it. Some of the industry, like cement industry, take any kind of waste, make them into a kind of a pellet powder, and then use their fuel today. So those things are cannot be processed here. Those wastes are processed there in a different way. And here the hydrogen production is through these techniques. And as you could see yesterday, I am very happy that Srikanth talked about it. I just want to highlight everything, anything and everything we do. Let us also connect that to the SDG, right? So the goals which are put out, sustainability goals, and map it. As you could see here, some of these goals are 6, 7, and 13, and you can just figure out what is there, what can be mapped, and so on. A quick glimpse of what is what in terms of hydrogen production and consumption. What am I doing in terms of time? Yeah, not bad. So in terms of production and consumption, you could see this predominantly the production is getting into the consumption of petroleum industry, the ammonia production, right? So into fertilizer industry and so on. That's what it is. A bit of methanol production, bit into electronics. One may wonder why electronic industry uses for cleansing. You must use hydrogen, reducing atmosphere. Some kind of hydrate formation could be there for some application and so on. And of course, metal processing and fabrication, welding, acetylene welding. Similarly, there are some cases where hydrogen can be added as a kind of reducing gas. It will be used in the furnaces for some application and so on, right, for reducing gas and so on. People try to talk about hydrogen for use in the vehicles, CNG blended with hydrogen today is being the talk, right? So most of you would be aware that up to 18% of blending of hydrogen to CNG is officially permitted, and it will be mandated very soon. Unfortunately, the fueling stations in the country, they do not have the hydrogen outlets. We don't produce hydrogen at that level, and hydrogen piping is not available. Hence, they are selling as only as CNG. But eventually, hydrogen will be coming in. The challenge is hydrogen today is costing anywhere between say 200 rupees a kg for a gray hydrogen to as high as 500, 600 rupees a kg of a green hydrogen. And your LPG is a CNG is costing something like 80 rupees a kg. When you blend 20%, roughly your fuel cost is going to go up. People will start questioning, but that gives immense benefit in terms of combustion emissions are virtually eliminated. I mean, are the minimized significant reduction in CO2 and so on. But as a policy, government to do that very, very soon. On a similar tone, you also are aware that petrol today is blended with 20% ethanol and it's being pushed to 30, right? So soon you will see 30. All of us know we get a big hit in the mileage. Vehicle is that was giving 16, 18 kilometers, per liter. Today is giving 2, 3 liters low. It's just because of ethanol. People may try to defend. We are doing good to the environment, yes, but ethanol is pretty cheap, cheaper than petrol. Petrol prices are not compensated for the oil prices. Again, it's again geopolitical. Let me not go there. But the point is that the utilization of these in these domain fuel cells or turbines or the other area is less than 2%. All these are big. So sometimes cosmetics for skincare, bit of small hydrogen is there, and food processing, agro industry for some of the fertilizer additive kind of thing people use, right? So the production route also, if you look at here, predominantly it is all coming from the routes that we talked about earlier, be it black, brown, predominantly, and some people have started looking into partial blue, right? And electrolysis today globally, it's just less than 3%, 2%. 4 is the kind of an estimated higher value, but remember, this is small. And look at this map globally, the production rate as of 2021 or 22. This slide, 31.1 gigawatt. The alkaline electrolyzers and the PEM electrolyzers, as we talk about the two different variants, and we today we have got AEM also into picture. So globally, if you look at, there are a few players at different levels, and of course, Ohmium, for its start only in the recent times, last 5, 6 years, they have found a place big, which means all the other players like Siemens and so on, they have been in the industry. Siemens has energy in multiple domains; they are also into it. But many of the players here, Plug Power or Ohmium, they are all into this, doing this, as a kind of new thing. We see some of the players, global players in India, but India per se, we don't have any big players. So this is a very simple schematic of integrated, the fuel cell. I mean, sorry, the electrolyzer setup that you saw. And talking about the technologies very briefly, I'm sure that you would have had a good session earlier on the technologies per se. But this is always good to have when you have a 4 or 5 days of FDP. In between, it happened to be a middle day, so it's always better to do a quick recap as to on the different kinds of technologies available as to the essence of it, right? So alkaline, PEM, and AEM are the three technologies that are being talked about today big time. Alkaline is very well established, known for its the cheap rates. It's inexpensive, I should say, reasonably safe. Uses simple materials at anode and cathode. It does not call for any big end membrane. It's a simple separator, as in a chemical processing unit. It's zirconia. Coated. The membrane, which is again a polymeric membrane that takes care of the system, and the operating voltages, current density. You could see that at low current densities, the yields can be lower, operates at relatively low pressure, and the purity levels are on the lower side. This after doing a bit of deoxo, so oxygen removal and a bit of removal of the alkali products. Typically done with the highly alkaline chemistries. 6 molar, 8 molar hydroxide chemistries typically operated at slightly higher temperatures as well. On the other side, the PEM is very unique, uses water, and I put the word acidic here because some of the ingredients in the uh, what is called as um, the membrane. So some kind of reaction leaching leads to acidification, and the water becomes acidic. It should have a very high conductivity. Impurity levels should be absolutely no, right? And they use quite a bit of expensive material. On the cathode, uses platinum and palladium, and on the anode side, even more challenging, expensive oxides of iridium and ruthenium for the OER, oxygen evolution reaction, to happen at the controlled condition. Right? As all of you know that oxygen evolution and hydrogen reduction are the reactions happening at these two places when water is being electrolyzed. Right. So we use a membrane called Nafion. DuPont manufactures it, monopoly, pretty expensive. It comes in different thicknesses, and delay time is so high, you don't get it off the shelf. India, if you want to do it for research, yes, there are some challenges. They don't give it just like this. If you want to do it for industry, yes, they want to promote business at the price point. And again, if you wanted to understand what it is as a chemist or as a material scientist and want to do a kind of a postmortem and understand the chemistries, do re-engineering, reverse engineering, you need to work with industry, get some samples, and then do it. Sometimes they don't normally give it for small levels for the academia to get it. That's a challenge. There are other membranes that are available in the country from different sources. I mean, from different countries. Agents are available, but again, the reliability and the kind of performance have to be mapped. It's not that easy. So, being a new domain, one has to really be clever and thorough with the subject before plunging into it. So, operates at the higher current density levels. Today, we talk about going up to 3 amperes per centimeter square. Remember, that's a huge number. That's a huge number. The advantage with the PM is that the purity levels are.
Actually, 70 kilo இருந்த மேல் டெக்ஸ் வரும்போது
Madam, can you please mute?
அதோட அதிகமா இருந்தீங்க நடுவில்
Excuse me. Thank you. Yeah, so the key point is that these PEM fuels, PEM electrolyzers can produce extremely high purity hydrogen, which are again, mapped to the regulations. I use the regulations, and this can directly go into the fuel cell. They are operating typically at high pressure. Obviously, when they operate at high pressure, always a challenge. Look at the last one. I'm not going to explain. It is an intermediate of these two. It is the price points are much lower than PEM, and the performance is relatively much higher than alkaline, closer to PEM. Hence, AEM is getting a lot of attention. Look at the anode and cathode material. They are mundane material, not so expensive. And some of the high-end AEM systems are with platinum and palladium for the kind of performance metrics. A few companies in the globe are into it. The purity levels can be higher, 99.99, and still it has to be further purified to 99.995 before that can get into the fuel cells for operation. There are other technologies like the solid oxide electrolyzer cells, high temperature from oxide chemistries. I know they have much higher efficiencies, but we need to understand the system more holistically from a larger production scale. A lot of work is going on, not yet ready. Membraneless is another concept. A company, a startup, we worked with them for a short time, but the technology is not yet ready. Maybe you can show it as a kind of a technology that can work. But yesterday you was mentioning about this as a big thing, and of course the team that have done a great job, starting this idea from some literature and then building it. But they have a big task in their hand to take this forward. So the technology is not yet fully mature. We have opportunities to take it forward. So this talks about the performance versus cost versus safety. As you could see, the PEM is expensive, cost wise high, performance is high, safety wise it is certainly, it can be taken care of, and so on, and the other parts are described there. So this is how the industrial level, the system would look like. When I say industrial level, we are talking about production rates of the order of the few hundred tons per day. So that's of hydrogen per day of quantum using megawatt kind of electrolyzer capacities. So the stacks will have a low pressure, high pressure side. Electrolyte will flow through. In this case, it is the high pure ASTM water, as they call type 1 water, with the absolutely controlled conductivity levels. The millisiemens per centimeter, microsiemens per centimeter numbers specified for the application need to be met with. You must use the right kind of membrane. It is a kind of a stack. with 10 cells, 20 cells, 100 cells, and so on for building 1 kilowatt, 10 kilowatt, 100 kilowatt, or a megawatt. It's going to be a scaled up stack. You will see the slide later. And as it goes inside, water can be split at 1.23 volts theoretically, but in reality you require a much higher, and then you require a specific quantum of energy to be spent to generate so much of hydrogen, right? So those numbers are available academically, you can look at it. So as the hydrogen and oxygen get split, oxygen can be processed. There can also be a crossover, possible crossover. There can be small amount of hydrogen there. That should be controlled. That's a safety issue, because hydrogen getting into oxygen side more than 4% can cause explosion. So we call it as what are called as lower limit indicators will be put up, and then ensure that the crossover is minimized and then done. On the hydrogen side, even small amount of oxygen comes in, it is okay, because you'll have a deoxo unit. The oxygen is taken care of, and then subsequently it will be heated up. It will be made to go through a kind of a system, a drying system, and also if required, there is going to be a what is called as a purification system with the kind of chemical reactants put there, and ensure that the hydrogen, whatever is coming out of it, is absolutely dry, and as well it's going to be 99.995. So if it is a PEM electrolyzer, it's going to be 99.995 straight away without anything. But if there is going to be other things, you must introduce all these things in place. That will make the system a little more expensive. And in the process, you also need to know that hydrogen cannot be just like that let out. Hydrogen being a light gas, it has to be compressed so heavily to be bottled. I will talk about that in a while later. And that's again a challenge the industry is having. So looking at that from academic perspective as a kind of a line diagram, a drawing, this is how it is, and then you can figure out these kind of drawings, available in the open domain. So understand how it is being done, what is the stack, how the connection is being done, what are the things that are required for the proton exchange membrane electrolyzer. You see suddenly a heat exchanger coming into the picture because it operates at high temperature. The reactions may raise the temperature. You need to cool it down, maintain it, and then the water is being recirculated. We call it as a polishing unit. It has to come back, and there will be the kind of moisture coming in at some point in time. You need to remove that. So all those things are a bit of engineering for getting the gases out. Hydrogen is separated out, and oxygen let out, typically free. But today, post-COVID, people are also seriously thinking of oxygen at whatever purity level, take it, and then if required, convert them into medical grade, and then make use of that. Let us not allow that to go. It also becomes a part of value chain as the byproduct and so on. And one of the key things industrially as a challenge is that how do you manage your footprint? So you'll have a small area over which you need to put. It is not that it's going to be given so many acres of land to put it, and that's the challenge actually. So one of the key points is that people try to look at modular construction, and of course safety is the utmost thing here. A small kind of a miss can cause a very serious explosion of hydrogen, and of course all the safety precautions. The hydrogen generation room, handling rooms should be with the electrical fittings which are flame proof and allied, and all that is pretty critical. So including the hydrogen storage vessel that we're going to talk about, either as a cylinder or a large scale, the kind of the canisters, or kind of these kind of large cylinders that are being transported either through ship or road. They have to be again very, very carefully designed, and then you need to use them. So footprint is critical as you try to do it in lab scale with a beaker or in a small setup. Looking at the industry, so it will be altogether a different ball game. Scaling is not a small thing, and the challenges at every point to regulate a leak, even a drop of electrolyte seeping from one point can affect the overall efficiency of the plant big time. Similarly, a lag leak from a small point may become catastrophe in the system, which means that robust engineering practices need to be applied with the involvement of all the practicing engineers, right? So mechanical, chemical, electrical, all guys should be there, right? Materials to be placed for at a system level thing. I'm not talking about individuals. We'll go there, get to the specifics in a while. But at a macroscopic level itself, we require huge things. So looking a bit microscopic, we are not going into the nanoscale. I'm stopping at one level. So here, this is what you call it as a stack, which is going to be constituted with the multiple ingredients. A membrane, which is the heart of it, right? So which allows the hydrogen to cross over by the process of splitting H plus ions with the proton exchange membrane we talk about. That's a special membrane with a given thickness that should have specific qualities and so on. We'll talk about that in a while. So we need to have a layer called as the diffusion layers, or the porous transport layers, as they are called, made out of specific chemistries with the layers, coatings, metallic systems, given the acidic nature inside and so on. I'm not here to talk about the chemistries and details. That's a different ballgame. My intent is to give you a flavor as to what all one has to look for to understand more holistically. So the catalyst on the membrane, it can be directly applied on the membrane. We call it as catalyst coated membrane, or it can be on the carbon papers coated on the other side, made as what is called as MEAs, membrane electrode assemblies. The processing of it by itself is a huge challenge in the industry, not easy. You require a systematic approach to understand the chemistries at a few milligram per centimeter square of loading of those catalysts, applying them by controlled processes, like screen printing or ultrasonic coating and so on. Lab scale is possible, but look at industrial level scale coating on a 2 meter by 2 meter. It's not that easy. It's always a challenge inspecting them, and then once you make everything ready, when you start assembling, you need to have the sealant and gaskets. We all know that the gaskets used in the pressure cooker works charmingly for say 2 years before it gets hardened, and then you throw out and then change it. But the gaskets, sealants that are used here for the assembly are different beasts altogether, not that easy. You must understand the chemistries, compatibilities. These are all pressurized systems. There are temperatures as high as 80°C in the system. And some of the gasket materials, are polymeric in nature. You need to understand their glass transition temperature, utilization, and so on. Bipolar plates, which are heart of the system, similar to membrane, through which the gases are going to be passed through. A small passages engraved on a plate. We call it as unipolar or bipolar plates, and they are thin plates. Can be made out of graphite. It can be made out of metallic material. They must have appropriate coatings for conductivity. The internal resistances cannot be there at all. It should be highly conducting. You may be asked to quote platinum or palladium or gold for that matter to eliminate the resistances as you stack multiple things together, and then as you stack everything, there are end plates at the end. They are you can see them with a stud on either side, which is just bolted assembly. It may look simple, a mechanical bolt and nut, but the challenge here, only if you put your hands on it, you will understand the challenge. It is not easy at all. Despite doing this for 2 years, folks are struggling to disassemble and assemble second time when they find some challenges inside. And as you do the end plate, there are going to be current distributors coming in here for the flow of current for the electrochemical process splitting to happen, and the stack assembly is absolute charm mechanical engineering. You must know what is the torque that is required, what is the kind of alignment, what is the kind of misalignment that is permitted, what kind of gasket sealing to be done, and then post thing, what kind of test to be done, the kind of hydro test at different points, at what pressure points, all that are being declared very clearly by the protocols that are available for these technologies. So a few information on the material requirements. It is not exhaustive. I'm just trying to give you a flavor. As long as the subject is easy to you, you can lay your hands in everything. But otherwise, you can go into the specifics and collaborate. That's the point, right? So if you look at the membrane, you are expected to know the thickness, whether it is going to be 20 micron or 50 micron or 80 micron or 200 micron. So depending on what kind of control that you got, what kind of price point that you got, and what kind of purity you want, all that. So it's all about the kind of price, cost versus performance. But at the end of the day, the membranes of specific chemistries, we talk about, the PFSA chemistries, right? So again, they're all the sulfonic acid group added membranes as the kind of for the specific proton conductivity you're looking at. Again, the numbers are specified, so many millisiemens per centimeter. The conductivity levels are indicated at different temperatures and so on, right? So we need to be sure of it if you are looking at alternatives and so on. And when you say, I've got a thickness, I've got the proton conductivity, is that the end of it? No. So always you need to look at the mechanical integrity and stability. You must have the material should possess adequate strength. While handling, it should not tear, shear, whatever it is. It should possess adequate stretch, elongation. It can be 100%, 200%, 80%. Below that, there can be a challenge. Above that, there can be a challenge. So you need to find out for this material, for this strength, what could be my elongation under the conditions. Is that enough? No. I need to understand when it is being operated, the reaction that happens inside, we will be under wet conditions. Even in the electrolyzer, water comes into contact. In the fuel cell, hydrogen and this combine to produce water. So in both cases, whether it is electrolyzer or in the fuel cell, you produce, kind of wetting of it, and because of it, these membranes start to swell. When they swell, they lose its mechanical integrity. Similarly, the membranes are meant to be good at low temperatures from the mechanical strength point of view, good in terms of proton conductivity at high temperature. That's why we wanted to go to 70, 80 C for getting the benefit. But not all membranes you can operate at high temperature. Thermal stability may not be great. So we need to have a trade-off between all these to figure out what membrane to be used for what electrolyte for what kind of power levels and hydrogen generation. Other than this, I am also concerned about the corrosion resistance of the materials used inside a system. It can be alkaline or acidic, as I said. Alkaline in the case of alkaline electrolyzers, PEM, it's going to be acidic. And there are enough of metallic components here. Graphite even could be there inside, and there can be situations of galvanic corrosion inside between metallic materials coming into contact. You have to be very, very careful because most of the electrolyzers that are being designed today, they give a life of 10 years, right? 80,000 hours is the typical number they say. Once I fit this everything, fit and forget is a statement people say, and of course for which the corrosion resistance need to be carefully managed. Performance in life, of course, it is needed. So in the interest of time, I will skip this with only one statement. If you look at the durability, the performance of these membranes have to be absolutely brilliant. If you look at the potential being measured, 1.7202, 1.7239. So the third decimal change over 2000 hours is the indication that the system is extremely stable. The fluctuations are going to be high in the second decimal or in the first decimal. You're going to have problems, right? So the third and fourth is said to be excellent. That's how you qualify the system. Similar is the case for understanding the performance. We do something like this. So in terms of material selection, I told the parameters or rather the property requirements. And this slide, I'm just telling you the anode catalyst layer, is going to be very, very critical because this is a vulnerable point, a sluggish reaction, diffusion reaction, OER, and for which we need to provide impetus. We need to have adequate quantum of iridium or ruthenium oxide, and look at all these. So from the price point, it is very high. From the microstructure, it has to be extremely controlled. It is not a metallic microstructure. It is a microstructure at a chemical level, at the surface level. How do you distribute so many milligram per centimeter square? 0.5 to 1 milligram per centimeter square is the loading of those catalysts which are being spread with appropriate ionomers in place. And if you look at the activity, how they are active the moment they are into it, so the state of activation is critical. How durable they are depends on the purity of the chemistry, how they are synthesized, how they are formed, condition they are exposed, and eventually all the time we look at alternative materials from the performance and the cost perspective, of course, durability will be kept in mind. So this is the one segment which is having enough of scope for research for people to look into. Of course, people talk about this big time because am I audible? Hello?
Yes, sir. Yes, sir.
Okay, I skipped the slide. So quick glimpse of what we have done in our facility. We have a program that was run with the oil consortia. So we made hydrogen electrolyzers, two systems. One is a membraneless stack, collaborating with a partner. They supplied the stack. We did make the balance of plant, what we call. So what you see inside is the alkaline electrolyzer. This is also alkaline, but this is membraneless, and then splitting of this will get hydrogen and oxygen. They are separated and then they are taken through the wall backside. This is the facility from this side here. It comes through the dryer and purifier. It gets into the compressor where you compress into a type 3 cylinder, a small cylinder, which is a 5-liter cylinder, which can hold a small quantum of hydrogen pressurized at 150 bar. So these cylinders can typically go up to 350 bar, but of course, for this project demonstration, our requirement was only 100 bar. We demonstrated. We are taking it forward with the other technologies. We are working on both AEM and PEM technologies today. So oil and gas industry is pushing 10,000 tons per, the production rates of unit at Panipat is big, and then oil and gas industry, especially IOCL, is pushing for the vehicle integration and electrolyzer market in India. As you could see here, many international players. OMIUM I just put on top because he's an Indian settled in the US driving this. L&T, of course, is an Indian company, but barring Reliance, Adani, of course, the other fellows will come in, right? So many other players are also into this. And see here, even though we talk so much about hydrogen market, today it is insignificant as we speak at this moment, and the jump that we talk about is close to 95%. So that's what I'm saying. Whatever we see on paper may not be the reality. We need to just do a deep dive, and then even yesterday's discussion, some of the statements on the funding, the growth, and so on. You have to be very careful and in deciphering it and take it forward. But the question is whether 25 to 30, this kind of a jump will happen. Yes, we need to wait and watch because we have technology, we have got quite a bit of investment. There is a push from government. There is a big involvement from the the what do you call the global partners, MNCs. Obviously, it is going to go forward. So, looking at the cost perspective again to ground ourselves, today India is targeting 200 rupees, right? So 180 200 rupees as the price point for gray hydrogen with all PLI incentivized stream that's available. So gray in many plants that's at that level, and green with a lot of incentives. We are targeting 5 to promote, make people get in, and probably at that point in time it can also get stabilized, right? So I wish it is not like the Geo phone when they were introducing 1 year it is free. After that, we know what happened, right? So I wish similar things don't happen because the Western world, the yellow and green, you can clearly see them. They are on the higher side. Many countries, European countries, are always on the higher side because a small country population is less and they need to pay more and they are higher. Some of the countries where the population is high, technology is mature, they are on the lower side. But all said and done, Indian numbers are unrealistic, is my opinion. This is the data that I compiled, spending some time just presenting it. So a couple of thoughts on the hydrogen cylinders. One on the type of cylinders, one, two, three, four, five. Typically, we talk about up to four. Still a monopoly in India. There are a few companies that buy and sell. Luxfer Corporation is the one that supplies hydrogen predominantly, including the regulators we don't get in India, unfortunately. So as yesterday the speaker mentioned, shared some information, metallic with wraparound only on the hoop side, and on the type 3, all sides, all directions. Type 4, the metallic part is off, and then you go into a plastic liner, which is into polyamides, HTPs, and so on, polymeric material, and it's completely type 5. It's still picking up, not done, even in globally, not big yet, and all composite winding techniques people talk about. So from glass fiber to carbon fiber techniques being talked about here, from pressures ranging from 150 bar to 350 bar to 700 bar and beyond are those hydrogen cylinders. Again, there are restrictions in terms of how much of quantum, in terms of kg, what pressure, and so on. I just leave it to you to figure out. I skipped this slide in the interest of time on the hydrogen safety and embrittlement. If there is an opportunity later, I will be able to talk to the relevant folks. Do you have another 5 minutes to conclude, sir? So, Swami.
Yes, sir. Yes, sir.
Thank you. Sorry for stretching, but I'm more or less
No
done.
problem, sir. No problem, sir.
Right. Right. So having talked about this, the reason why I use this slide here, other aspects of the value chain covers all the aspects from production to storage to utilization. So I just wanted to highlight some of that. So on the fuel cell front, the government is now pushing big time, trying to get into the uh, segment, three-wheeler segment, the vehicles that are being run with lead acid batteries or lithium batteries today. We do not know about the future of lithium unless somebody comes out with a solution for the reprocessing, recycling of lithium. And lithium risk has been mitigated big time. We don't have much of the fire accidents and so on. Fortunately, we are good, but we do not know after a few years what is going to be the utilization. We can't dump lithium. Another challenge. We need to understand that. And in that context, green technology is being pushed. This is expensive today, but eventually government will have a say pushing it to the common public. There is no way we can avoid. So PEM fuel cells are just the reverse of the electrolyzer. Electrolyzer, we put water and then split into hydrogen oxygen. Here you put hydrogen and oxygen under controlled condition, control stoichiometry, make them grow, and then with the right kind of catalyst at the anode and cathode, you make them combine to produce water and power, and that power is being utilized for the mobility applications, stationary power, and so on. So we had a program running for the 4 years. We have some of the things indigenized. We still have the chemistry is bought out from outside, but synthesis of some of the catalyst chemistries are done in-house. Membranes, for some aspects, we are trying some indigenized technologies, working with CSR labs, not on this, but some other technologies. The bipolar plates and so on, we have indigenous sources as well. We are trying to work on metallic systems. We have a full-fledged facility for making stacks. So this is a 2.5 kilowatt stack that is being built. What you see in the picture is a 5-cell stack of very small capacity and a 45, 50-cell stack of 1 kilowatt rating. And the larger size stack with a similar size or slightly more number of electrodes, we have made it for 2.5, uh, uh, which was offered to the oil consortia recently. On the hydrogen value chain, one of the big things globally, the industry is looking into using this in the kilns. So the calcination kilns use pet coke and what they call it as AFR, alternative fuels. All kinds of dumped waste are being fired inside with the calorific values ranging from 1,500 to 2,500 kilocalories per kg. Pet coke is 8,000, and this is about this number. They are able to fire this in those kilns for calcination process for the cement industry. Fortunately, all the junk that they use, they go part of cement without impairing the behavior, performance, properties of the cement they produce, because they produce a variety of cement for a gamut of application. So that's where the industry is. Similarly, the Indian steel industry is being pushed to take the DRI. A blast furnace uses small levels. Those who are familiar with metallurgy would understand this, but the industry is now pushing the hydrogen industry. When I say steel industry is pushing the hydrogen industry to demonstrate the technology at pilot level and deploy, they are ready to take for DRI, where you will see significant emission control. Millions of tons of CO2 emission can be taken care of big time. One of the thing is that you may be aware that there is a concept called the carbon credit, and for every ton of CO2 emission minimized or eliminated, there is an incentive. In the Western world, 1 ton of CO2 emission eliminated, you will get 100 euro as the kind of credit for your industry. So when you talk about millions of tons of CO2 eliminated from one plant, one line in the cement industry in 1 year, you can imagine how many crores of revenue they can get by just by minimizing the carbon emission. That's where it is getting incentivized. Hydrogen costs are higher. Still, the math is being worked out to figure out if they can do something. Same extends to paper and pulp. People are looking into it. If you have got any thoughts and ideas, these are the ideas that you can get into for research proposals. I skipped this in the interest of time. Yeah, so this is altogether a different talk. This is again for the hydrogen chain. It is relevant. It should be integrated. But today I don't have time. I don't want to step into the next speaker's time. Sorry about it. The summary slide, what you see here is that pretty simple, straightforward. It's taken from the open literature, not mine. I should thank people, for posting a lot of knowledge in the open domain for us to learn, also share with people, and whatever little thing that you do, please acknowledge the source and then understand, transact whatever learning that you got. So the message from this slide is that we talk about green hydrogen big time from different things, including nuclear. They call it as, instead of pink, they are integrating this to green because similar lines. I don't want to differentiate. Where there is going to be a CO2 coming in sequestration, they call it as blue. This gets in, and eventually the entire value chain from storage to distribution to application has its own opportunities. And more than the opportunities, I would say opportunities are up plenty. We have progressed significantly in the last 2 years since the announcement of 2023, the mission by the government. Many people have started, many academic institutions have started to look into, but as opportunity, people have grabbed it. But as challenge, how much we understood, how much we are equipped today, we are equipping ourselves to solve the problems, to mitigate the challenges, to sail through in a collaborative mode. I still doubt. I'm not sounding skeptical, but I'm saying unless otherwise you are sharp, you are committed to your own learning and then giving back to society, problems like hydrogen cannot be solved. So this is a clear kind of explosive problem like hydrogen explosion, a burning problem like hydrogen firing, right? It is all up to us to figure out the right way, form the right teams, acquire right knowledge, produce right skill sets, people with right skill set, and then forge alliances in right ways and take it to the technology level as 4, 5, 6, and then we call it as TR levels, and then take it to the MRL. So working with industry is always going to be helpful. I being an academic for about 15 years, so 8 to 10 years initial phase with NIT Trichy, and about 7 years at Shastra University. I've been teaching in metallurgy and mechanical. These subjects are close to my heart. So apparently, I could also I could talk to many people. Many have educated me on many fronts. What I spoke today is not my knowledge. It is the knowledge given by many people. I thank all those people that have, enriched my learning in whatever little I shared with you. Right. With that, I stop for the day. Ladies and gentlemen, really appreciate. Thank you for your patience. Sorry for the stretch. I thank Professor Swami and Dr. Bhargavi for having me in this session. Thank you so much. Any questions?
Yeah, thank you,
Thank
sir.
you very much. Thank you, sir, for your valuable information and the industrial scenario and for explaining everything. So, open to questions. The session is. Can participant ask some questions?
Madam,
Yeah, please go ahead.
sir, can you share this video for this session also, sir?
Yeah, we are recording. We will share this session.
Okay, sir.
I'd be happy if there are at least a couple of questions.
I think any questions from the participants, please rise. These are industry experts.
The teachers are there, many teachers. They should actually promote the culture of asking questions. Good, bad, ugly.
Yes,
It is
yes,
okay.
yes, sir.
I'm surprised.
Sir, one question is there, sir.
Go ahead.
Sir, you have said in cement industry that we are utilizing powers.
Utilizing?
In cement industries, we are utilizing power, you have said, no, sir?
Cement industry uses pet coke as the firing thing. So pet coke firing is expensive, and hence they started using alternative fuels. Alternative fuels are just junk, all solid municipal waste, from plastic to rubber to anything that you name can be taken. They are actually crushed, pelletized powder form. They are also subjected to co-firing.
Sir, is
That in
it
a way, no, 1 minute, let me complete this. So one of the agenda is that cement industry is power intensive, energy intensive, and if they can use, because of course CO2 emission is going to be more there. If they can use hydrogen, hydrogen has a much higher calorific value, 40 megajoule per kg for methane, 33 for pet coke, 120 megajoule per kg for hydrogen. So 3x. And once you can fire in small quantum also, your emissions are eliminated, thus by carbon footprint reduced and the carbon credit is coming into picture. So when countries signed up for the net zero, many of the big industries sign up for net zero yearly. And if they show carbon credits, it's a big thing from their side. So instead of conventional fuels, there is a push in the industry, both steel and cement, to look for hydrogen as a fuel for firing. That's all.
Sir, is it renewable energy or non-conventional energy sources, sir? If we use hydrogen.
Yeah, when you okay, good question. So if it is going to be there, that hydrogen should be only green. Yeah, unless you produce a green, you are not. Otherwise, you produce from gray or brown. You produce that expending some carbon there elsewhere. It is something similar to electric vehicle. Electric vehicles are on the road and you are charging using a grid. So it is not truly 100% green unless you are going to have a, you know, renewable based hydrogen. That's where the push. When you say 500 gigawatt of hydrogen, I mean renewable energy pushed by 2030, there is also a mandate by the government wherever there is going to be a solar or this one wind, they will have electrolyzer, they will have a storage facility that can be BESS, lithium based, or it can be vanadium redox flow battery. I had a few slides to talk about, but in the interest of time, I did not do. So which means that in case of power availability, you can send it to the grid, you can produce hydrogen, and the excess power you can store, and the stored power can be reused for hydrogen production when the wind is not available or solar is not available, which means it is completely green.
Sir, last one question, sir. You have said this you can use hydrogen, but is it production will be higher or low, sir?
Which production? Cement production?
Cement production. Cement
Yeah. So
production.
yeah. So hydrogen, as I said, it has got a higher calorific value. We need to have right proportions. The temperatures inside the kiln are typically ranging between 1400 to 1000 in the kiln, right? From exit to entry, if you go from this side to that side. So the chemicals will be coming from the other side, and your flame front is from here. When you use hydrogen flame front, they are going to be hotter. And of course, the process has to be done in such a way that it does not affect the heat balance. It should not affect the productivity for that matter. Without compromising on the quality performance of the system, we should be able to use this at appropriate price points, eliminating emissions. So Google
Okay, sir.
out CII initiatives, cement industry, alternate fuels, AFR. If you are a chemical engineer interested in this cement industry, Google it out. The Confederation of Indian Industry conducts conferences very regularly, and they talk about this big time. AFR is the one normally talk big. Hydrogen is being mooted by different corners. The last 3 months, 4 months, quite a lot of discussion happening on this.
Sorry, sir. I have worked in cement industry only itself only. So I have asking,
Okay.
sir.
No problem. No, if what I said is not actually aligned with your experience, you can also tell me what it is. I'm saying based on what I have seen in the industry and what we have been trying to do in the industry, right? So,
Sir, I
yeah.
just have a question as you have so much industrial experience and also experienced person. So how do we see this green steel, sir? How can we, how can we apply this hydrogen in the steel production and how it will affect the productivity? Can we really see this transition in
It has
steel
to happen
industry?
because hydrogen you see only as a source of energy. So today, if you are, for firing, if you're using conventional fuels, and then for reduction, the entire process, the steel industry per se, from steel production, iron and steel processing to heat treatment, every segment there is an opportunity for hydrogen firing, right? So as a typically we use that in furnaces for reducing atmosphere and so on, ammonia being cracked to get into this and so on, right? All of us know, but today, with the hydrogen push from the context of CO2, people are seeing the opportunity with DRI, direct reduction of iron with the hydrogen is the possibility. In the olden days, also they used a very small quantum of hydrogen in those blast furnaces and so on, but beyond a point they could not use. So there is enough of impetus in the Indian industry to look into. R&D is slowly getting started. I do not know how long will it take, but eventually next 5 years will let us know, right, as to are we going to have adequate quantum of hydrogen as we talk today. We want to produce 5 million metric tons of green hydrogen for that application. One. Then is this hydrogen available on site on demand? Because depending on the quantum, you cannot transport. Transportation is a huge challenge. I did not talk about that. Otherwise you need to produce that ammonia, get there, crack it, and then use it. So that's a challenge. So there are plants that are being put out on site, on demand, high-end electrolyzer available. And if that is going to come in, coupled to the available solar power or wind power within the large industry, which of course they have done based on the mandate, there is every possibility. Proof of
So
concept to be done. And
why I
yeah,
have
go ahead.
asked this question is when I have visited DRA based plants, so they are actually first they are using some green basis fuels, but later on because they cannot afford it, so they are shifting to again coal. Even in DRI also they are using coal. That's why I wonder when this will be possible or what are the challenges,
So,
major challenges with it.
yeah, it's all about value chain, as I said earlier. So it's all about production is one part of it, and the production mapping down to storage to utilization. One has to be clear as to what it is. So as I rightly said earlier also, you cannot really transport hydrogen for such voluminous continuous production plants. So because it's a light gas, you require in more quantum, and if you require say 100 kgs per hour, the amount of hydrogen required in meter cube is going to be so high. So which means that you have electrolyzers running continuously supplying there. There are plants which I know of where your biomethane production from the waste is being put into the furnace on a regular basis. In a similar fashion, you must have electrolyzers put up large scales and then coupled to the steel plants. From outside, getting in kind of cylinders, canisters, feeding is ruled out. It is not like one another fear. Not possible at all.
Sir, as you have mentioned, so now that it is a topic of sustainability and from waste to giving valuable products. So there is a concept from waste to hydrogen energy also. So do you
Yes.
have any suggestions on that, how the research should be done in this area?
Is available, in many open literature. You can look at it. I just mentioned about it. You can go and Google out Indo European Union EU Horizon call was made September this year, and the proposals were from across uh, the European countries and India with a consortia. And the mandate was the biogenic waste, which is non-usable. So at the end of its life, and then you try to make use of it. So converting them into useful hydrogen by different techniques in different stages, including plasma techniques people talked about, right? So photochemical, thermochemical, and char, this thing, gasification at high temperature, all that. There are a gamut of techniques. People talked about getting these waste, getting them into pellets, and then mapping them by using the GPS techniques, coupling that to artificial intelligence, map the quantum of this thing, make what is called as, I don't remember the term, terra something, making them into small like pellets, tablets kind of a thing for feeding, for firing, and so on. Right. So that is a big time happening today. There is a push in the country as well.
Yeah, okay, sir. Thank you for valuable information.
Right.
Sir, good evening, sir. Hello.
Yes, sir. Please. Yeah, Professor
Sir,
MK, go ahead.
sir, I am the mechanical engineering. I have the background, so I want to enter into the green hydrogen production. Could you give me the directions? So where should I what?
Green hydrogen. You want to understand green hydrogen or get into green hydrogen production?
Actually, I have done the work related to the wind energy, sir. I have done the wind energy.
If you have done. So
Pitch control of the origin wind turbine. So now I have the and what are the ways are there for mechanical engineers to do something?
see, with your domain expertise, you understand the wind space. You know
Yes, sir.
how reliable the wind is. You can create a wind farm working with people, or you can go to a wind farm, ask them to put an electrolyzer over there, and then
Yes, sir.
use the wind farm. They have what are called as how much of thing that should go to the grid during the regular time. There is a peak time, right? And peak shaving. There are multiple terminologies that they would use. You would understand.
Yes.
And excess
Yes.
power can be used for hydrogen production. So you need to have electrolyzer being set up in wind farms, and then use those electrolyzers for producing power using fuel cell, or
Yes, sir.
use that for other application either by transport or other means.
Yes. Sir, is
But
this green hydrogen production only for the chemical engineers? Otherwise, is there any other branch
green,
people
green,
can do
hydro-
some?
green hydrogen is a terminology where the emissions are zero. We don't have a greenhouse gas emission is eliminated. That is the reason why it is called as green,
Yes.
because it is done by a simple splitting process, right? So for that, the current, if I take from grid, it is not green. If I take the current from renewable, it is green.
Yes, sir. Yes, sir. Thank you, sir.
Yeah. Anyone else?
Yeah, any more questions from participants? I think there is no more questions from the participants. So on behalf of the NIT Raipur and ATAL, sir, I extend our heartfelt gratitude to Dr. Balsa Srinivasan. He is a general manager and High Energy Batteries Limited for delivering an insightful thought and provoking expert talk on storage and distribution challenges of hydrogen, sir. You have given a lot of industrial related and storage technologies and safety consideration, as well as some practical challenges in hydrogen logistic has greatly enriched our participants. So the real world perspectives you shared from the industry applications have provided invaluable knowledge to our FDP participants of mostly faculty members and some research scholars are there. We sincerely appreciate the time you dedicated to interacting with us and addressing our queries with such a clarity and depth. Your contribution has significantly added value to our FDP program, sir, and we look forward to continue collaboration in future academic industry initiatives. So thank you once again, sir, for your esteemed presence and for sharing your valuable things, knowledge to us, sir. Thank you very much,
Okay.
sir.
Oh, thank you, one and all, for the patient listening, and please do stay connected with the group, and share knowledge, and these kinds of platforms should be leveraged for the long run, also for the society. Thank you so much, everyone. So, Swami, thank you so much
Yeah,
for
yeah.
your invite,
Thank you,
and
sir. Thank you very much, sir.
so with your permission, let me just step out. I need to move on. Thank you.
Yes, sir. Thank you, sir.
So please share your video, sir.
Yeah, we'll share at the end.
Sir, session and second section also you have not shared, sir, still.
Can you just drop off?